So in this lecture, I want to talk about what happens when we try to do a Friedel alkylation with a secondary chloroalkane. So let's go ahead and get that in front of us. So with the secondary chloroalkane, so let's go ahead and look at an example that might be seemingly straightforward. Let's go ahead and take this plus benzene. Sorry, I've got things flipped around in terms of I usually put the chloroalkane first, but hopefully you can see that what we're doing is we're stitching this carbon that's attached to the chlorine into the aromatic ring. So will this work? The answer is maybe. Maybe. Okay, so what we have to rely on is this chlorine first reacting with aluminum trichloride to give a complex where the chlorine is attached to the aluminum, and now the chlorine atom that was once part of our carbon framework to be our super electrophile is now positively charged. Okay, so will this work as is? Let me ask this question. Is this too hindered? Let's ask another question. Will this occur? What if I have aluminum trichloride with negative, positive? So I'm going to take the same complex. I'm going to absorb the electrons from the carbon-chlorine bond onto the chlorine atom so that it's neutral. It's going to give us a secondary cation. Is it too hindered? Is this stable enough? And the answer is a definitive maybe. It sort of depends on the secondary alkyl that we're using to do this reaction. Like if we have certain substitutions, we could promote one aspect over another. Similarly, if we change the reaction conditions to maybe apply more heat, we could attack into a more hindered, but something that would result in not the most stable secondary carbocations. The answer is a definitive maybe. What I want us to focus our attention on instead is another interesting issue that emerges with some secondary chloroalkanes, and that's the issue of electrophile rearrangements. So instead of us just predicting products with secondary electrophiles, let's recognize that it's kind of a troublesome beast to know whether or not these things are going to react. There's a lot of issues at play. But let's look at this issue instead. Let's change our chlorine so that we have an isopropyl group next to the carbon bearing the chlorine. You'll notice that this carbon with the chlorine center is still a secondary carbon. It has two things in addition to the chlorine atom that are attached to it. Now what I want to do is attach this to a benzene by way of a Friedel alkylation catalyzed by aluminum trichloride. The expected product is this. The expected product under standard conditions is this. Expected, okay? But the actual outcome is a bit different. The actual outcome is one in which the benzene is attached to a different carbon. The carbon that I've been highlighting green is now over here, and we have a different connection point. So here is our new bond. And we get a product that is not what we expect. So this turns out to be the major product. There might be a competitive amount of this of the expected isomer. Those two things are isomeric. They have the same carbon count. But what sort of happened? To get this product as our major product. To answer that, let's look at the mechanism. So the mechanism for this transformation starts first with making the superelectrophile. Now, one of two possible things can happen, an SN2-like approach or a SN1-like approach. But either way, we're going to give the same superelectrophile to form. Okay, let's start with the obvious first step. That's going to be the chlorine adducting with the aluminum trichloride by way of one of its lone pairs of electrons. That's going to give us this species where positive charge is on the chlorine in the central atom. Okay, now we could have a couple of things happen. Let's do this. Possibility 1. The first thing that we could consider is we could have that adduct form the carbocation that's secondary. Is it stable enough? Tough to know. This one's not as stable as a tertiary carbocation. It's secondary because the carbon with the carbon with the positive charge has two groups attached to it. But it turns out that there's a hydrogen next door that can actually do what's called a 1-2 shift. To give a product where, or excuse me, an intermediate where the hydrogen is now moved over one position. It's moved over to that positive charge. It's neutralized that positive charge. In its wake, it left behind a positive charge at this position. This positive charge is now at a tertiary position. So we go from like a so-so stable carbocation in the secondary position now to a tertiary carbocation, all by letting that hydrogen move from one position over to another. It just walks across the molecule, okay? Now, when that happens, the benzene now has a new opportunity. The benzene could react with, I guess I'm drawing that hydrogen right away. It could react with this carbocation, which is stable, which is going to sit around a lot longer in the flask. Maybe that secondary carbocation was so unstable that it didn't wait around too long before it just pushed a hydrogen over to get to something that was more stable. Okay, when we attack this position, we get a positively charged intermediate that now has two methyl groups here and a methyl group down here, hydrogen over here. This is the intermediate that when losing a positive charge gives rise to the unexpected major product, two methyl groups, and that's what we observe. So the superelectrophile has undergone a rearrangement to give rise to a carbocation that's more stable. It's tertiary. Let's look at another possible way. So I say that's possibility 1, possibility 2. There's two possibilities. It turns out I'm going to leave possibility 1 at the top of the page just so you can see how similar they are. What's happening in possibility 2 is I'm going to go from the aluminate, whatever, the aluminum with negative charge complex, positive charge on chlorine. I'm going to let like a conservative event happen where the hydrogen shifts over, adds to the carbon bearing the chlorine, and then pushes off the chlorine. I don't know how I feel about this one so much. I've seen some things like it, but I feel like if you're going to go this far, you might as well just do an elimination to make an alkene, which could certainly happen. But if we do this, we actually get the exact same intermediate. The hydrogen's walked over and shoved off the chlorine atom. So I kind of like possibility 1 a little bit better, but once we're here, we're at that same intermediate that can react with our carbon atom. Okay, so the take home is probably possibility 1. It's forming an unstable carbocation that rapidly undergoes a 1-2 hydrogen shift to give rise to the product. Okay, so what's the take home message here? Okay. It turns out that with secondary and even some, but I'm not going to have you worry about it, even some primary chloroalkanes, rearrangements, and let me add carbocation here. Let's just keep it general. Chloroalkanes. Rearrangements can occur to form more stable cations. And what I mean by more stable is this is tertiary carbocations. Okay? Leading to unexpected products. This is not desirable. I mean, there are some times where maybe you get to a more useful carbocation, but let's look at this. Let's look at this previous example. We had a, and let me make note of this here. This usually the rearrangement occurs with a 1,2 hydrogen shift. We call it 1,2 because the hydrogen just moves over one atom, moves from atom 1 to atom 2, they say. It's that weird numbering system organic chemists use. Okay, so we go by way of a 1,2 hydrogen shift. All right, and what that looked like was hydrogen here, we have a plus charge here, hydrogen walks from atom 1 to atom 2. So it just shifts over. That gives a molecule where now the hydrogen and the positive charge have switched places. That's generally how these things work. It happens right next door. Sometimes even a methyl group can shift, although not often enough to where I want you to worry about it. Okay. So we went from a secondary carbocation to a tertiary carbocation. If you wanted to like set up this reaction, it's just kind of silly. Like if you wanted to go by this way, like if you wanted to start with the chloroalkane, the secondary chloroalkane, it's a little silly because why don't you just go to the trouble of making the chloroalkane where the chlorine's already in the tertiary position. You'll make a tertiary carbocation. You won't have kind of a weird mechanistic issue. You'll just make the carbocation and you'll get a single product. You're already at the most stable carbocation. So just use this if you want a product where you have that connection point. And by that connection point, let me highlight. If you want to connect the benzene to that carbon, just put the chlorine at that carbon. Don't try to hope that a rearrangement occurs that's favorable, because often it's the case that it's not that favorable. Okay, so this is generally viewed as a downside. Now, what do I want you to think about? I want you to be able to rationalize when an unexpected product is formed. Like I want to be able to give you a problem and be like, okay, so-and-so went into the lab. Dr. Willoughby goes into the lab, tries the Friedel-Crafts alkylation reaction, and finds that he gets this product that's unexpected. Can you rationalize why that product was formed? You'd show the mechanism for the formation of the super-electrophile that gave rise to the unexpected product. That would typically involve a 1,2 hydrogen shift. Let's go ahead and assume that if we have a secondary haloalkane as your starting material, it gives rise to a carbocation intermediate. So, okay, that's what I want us to be able to do. It's not like, this isn't a predict the product situation where I hand you some haloalkane and I'm like, all right, it's secondary, good luck. That's not fair. Okay, that's not what I want us to do. I want us to be able to rationalize why we observe unexpected products. Okay, so that's an unusual aspect of the Friedel-Crafts alkylation reaction. Turns out it's not an issue for the Friedel-Crafts acylation reaction, which is why that's often the method of choice. And we'll go over that in the next lecture. So till then, see you then.